In this video, let us talk about the tension splice. Tension splice is nothing but joining two plates. For example, we have to join a larger span. That length, in that length, required length, the pieces may not be manufactured in the industry. So in such cases, a single piece is not available for tension member. We have to join. So that joining is known as splicing, and the joining plates are known as uh, tension splices. These two are tension splices. We generally also call them as cover plates. So if the tension members are of different thicknesses, filler plates may be used to bring the members in level. See here, there's one plate, it has to be joined with another plate of thickness which is not equal to this. So in such cases, we have to use a filler plate to match the level. So that is known as filler plate or packing plate. So the clause related to packing plates is mentioned in IS 800-2007, that is 10.3.3.3, page number 81. So the design shear capacity of bolts carrying shear to packing plate in excess of 6 mm. So when the packing plate, if we use more than 6 millimeters, the shear capacity will be reduced. For that, we have to consider this factor, which is beta pk 1 minus 0.0125 tpk, and here tpk represents the thickness of the thickness of the packing plate. Let us see an example problem. Design a splice to connect a 300 mm by 200 mm 20 mm plate with a 300 mm by 10 mm plate. The design load is 500 kN. Use 20 mm black bolts fabricated in shop. So let us solve this problem. Here we can see clearly, if you see the cross section. So initially this is having 300, that will appear, that is a width, and this is 20 mm plate, and that has to be joined with, just a minute, it has to be joined with the 10 mm thickness plate. Here this is 10 mm plate and this is 20 mm plate, and both are having the width 300 mm. So we have to design it for the given requirement. So let us use the double cover butt joint for this. And also we are using the packing plate. This is the packing plate. We are using a double cover butt joint. Let us draw it. So in this manner we are providing this. So this is the initial assumption. What we are thinking of. This is the initial assumption. So let us see what actually is given. So the diameter is mentioned here, right? D is 20 mm, and D naught is its clearance plus 2. Here D naught is 22 mm. So we have to use the packing plate, which is 10 mm, to match with 20 mm plate. This is also 10 mm. So here TPK, the thickness of packing plate would be 10 mm. And here if you consider the thickness of thinner plate, that would be 10 mm again. We have to first find the bolt value in order to design the splice. So after designing, we have to find out the strength of the joint. So let us find it out. So first we have to find out the bolt value. So from this we have to find out we have to compare for bearing strength, we have to compare for shearing strength. So bolt value is the design strength in shear, VDSB and VDPB. And here VDSB is VNSB by gamma MB. And here again VNSB would be beta PK. So we have to, when we are using the thickness of, we are using the packing plates, we have to use this factor of reduction, FUB by root 3 into NN into AN plus NS into AS. So let us try to write what is beta PK. I will show you. on the code. Here it is. Beta pk is 1 minus 0.0125 tpk. So let us write it here. Beta pk is equal to 1 minus 0.0125 tpk. We have thickness of pattern plate 10 mm. Let us substitute 1 minus 0.0125 into 10. So we will be getting this value as 0.875. That is beta pk we got. What else we need? Here in order to substitute we need FUB. FUB we are using, we are assuming 4.6 volts. So FUB would be 400 Newton per mm square. And this is from codebook, page number 14, page number 13. Here it is. When you are using 4.6 glass board, this is the ultimate tensile strength, which is 400 Newton per mm square, or 400 megapascal. Okay, FUB we have written, and here NN we are assuming number of, here NN is, let me show you this. So it's a double covered butt joint. When the bolt is like this, it has two shear planes. So it will cut like this, here and here. So when it is cutting like this is one shear plane and this is one shear plane. So in the process of cutting, you know, the bolt will have some threading, right? So here NN indicates, okay, NN indicates number of shear planes cutting the thread part. So we are assuming NNL is 1. And we are assuming NS is also 1 because number of shear planes cutting the shank will be 1. So this is the double cover butt joint. We will be having two shear planes. We can assume one is in shear, one is cutting the shank, one is cutting the thread. So NN, NS we got. AS is the area of the shank, which is simply the pi by 4 d square. So that is pi by 4 into d is, we have 20 mm, that is 20 square. We will be getting it as 314.16 mm square. Then net area, we will be getting net area as area at the thread, 0.78 into AS. So that is 0.78 into AS 314.16. We will be getting it as 245.044 mm square. Now we can find out, these are all the parameters we require in order to find out V and SB. Now we can substitute it. So let me show you that. So in this we have to substitute. We will be getting it as V and SB is equal to beta pk, we got it as 0.875 into FUB is 400 by root 3 into NN we have 1, AN we got it as 245.044 plus NS we got it as 1 and area of the shank we got it as 314.16. So after calculating we will be getting the value of the nominal shearing strength. We will be getting it as 112,999.803 Newton. So what would be VDSP? This is a design wearing strength is nominal shearing strength, nominal shear capacity by gamma, partial safety factor for bolts when you are using ultimate tensile stress. So that would be W1299.803 by 1.25. So this gamma MB is from page number 30 of IS 800. I will show you now. So here it is. When you are using the bolts bearing that, gamma MB would be 1.25. Okay, let us get back. So if you do it, we will be getting the answer as 90399.8 Newton, 84 Newton. So VDSB we got it as 90399.84 Newton. So we need to find out the design bearing strength too. We have to take the bolt value whichever is less. So always we have to design for the lesser strength, because when we are getting the value of shear is more and when we are getting the value of bearing is less, we have to take the bearing value as a design strength. Otherwise, if you take this, the bearing part will fail. So you will understand with the numericals now. So bearing strength, let us find it. Bearing strength, it is denoted by VDPB. So VDPB is the nominal bearing strength or nominal bearing capacity, that is VNPB by gamma MB. So what would be VNPB? So that would be 2.5 into KB into D into T into FU. So this is also mentioned in page number 74 of IS 800. No need to remember all these formulas. All you can get it directly from the code book. Page number 74 this is. So KB is actually, let us find out all the parameters so we can substitute in this and we'll get the value. So KB is the smallest of, we have three values here. E by 3D naught or P by 3D naught minus 0.25 or FUB by FU or 1. Whichever is less, we have to consider it as KB. So here we are assuming the edge distance as 40 mm. So this is all assumption we are designing it, right? And pitch as 60. So edge or end distance 40 mm. Let us just substitute 40 by 3 into 60. We get it as, 3 into D naught is 22. Okay, we will get it as 0.606. And here it is pitch we are assuming that 60 by 3 into D naught is 22 minus 0.25. We will get it as 0.659. And here FUB is 400. We are assuming the plates as FE 410. So we will be getting as 0.975. And this is the 1. So the value which is lesser is 0.606. That is KB 0.606. So we have found KB, and what is the diameter of the bolt? We have 20 mm. What is thickness? We have thickness of the thinner plate as 10 mm. And FU is the strength of the plate, that is 410 Newton per mm square. So let us substitute all of this in this equation in order to get VNPB. Let us do it. VNPB is 2.5 into KB is 0.606 into 20 into 10 into 410. So we will be getting the value as 124230 Newton. So VDPB we can now find it out, right? VDPB is VNPB by gamma MB. So this is a partial safety factor. Just now we have seen from page number 30 of IS 800. VNPB we got it as 124230. By the gamma MB is a partial safety factor when you are considering ultimate load for the bolts. It is 1.25. So we will be getting it as 199,384 Newton. So here compare VDPB value is 999,384 and here VDSB is 90399.84. So what is less? This is less, right? So we consider VDSB as or bolt value as 90399.84. So let us just take 90400 Newton. So now we have to find out the number of bolts in order to design. What would be number of bolts? It is the design load by design strength. Design load by design strength. What is design load? It was given in the question itself. That is how much? 500 kilonewton. In order to convert into newtons, so it's 500 into 10 cube by design strength is 90400. That's the bolt value itself is the design strength. So we get it as 5.53. So let us approximately provide 6 bolts. So the diagram would be like this. Having 2 rows, 6 bolts for two sides. So we have to now check the shear strength of the plate. So we have actually designed now, and we have to check for strength of the plate. So when you are checking strength of the plate, that depends on again, it's the smallest of first one is the strength in yielding of gross section. So that is TDG. G refers to gross, D is the design. So second one is strength due to rupture in critical section, TDN. And third one is design in block shear strength, that is TDB. So we have actually two values, TDB1, TDB2. We have to take the lesser value compared to these two. So let us see the first one, TDG. That is the strength in yielding of cross section. So page number 32 of IS 800 gives this value. Let me show you once again. So here it is. So this is first one is design strength due to yielding of gross section. This is the value TDG. Design strength due to rupture of critical section. This is the value. And next we have to find out design strength due to block shear, which is having TDB values. Two TDB values we will be having. So we have to calculate all these values, and we have to take the lesser value as strength of the plate. So let us find it out. TDG is AG into Fy by gamma m naught. So what is AG? AG is the area of gross section. So 300 into thickness of the thinner plate we have to consider. So AG is equal to is the width, simply B into T. So B is 300 and thickness is 10. So that is 3000 mm square will be getting. And here Fy is the plate as a 250 Newton per mm square. Or you can also take 240. So that is actually mentioned in code book. So both are fine if you take page number 14. So here IS 2062 mentions if you take FE410, so that would be having less than 20 mm diameter, 250 Newton per mm square would be the yield stress. If 20 to 40, 240 would be the yield stress. So you can even take 250, no issues. So let us do it. 250 Newton per mm square. Gamma m naught we have seen from the partial safety factor page number page number 30 of IS 800. So here this is gamma m naught when you are resistance governed by yielding. Gamma m naught is 1.1. So let us write. Gamma m naught is 1.1. So we have these parameters to substitute. We can do it now. So TDG is equal to AG, we got it as 3000 mm square. Fy we have 250 Newton per mm square by gamma m naught 1.1. We will be getting the value as 681.8184 Newton. So into 10 cube Newton. So that is 681.818 kilonewton. So that is of course greater than 500 kilonewton, the design load given in the question itself, right? that is fine. So applied load is 500 and its strength is 681. So that is absolutely safe. So let us check the second one, which is the strength due to rupture of critical section, that is TDN. So second one, the strength due to rupture of the critical plane, that is TDN. So we can write it as, so again page number 32 of IS 800, you can check it, 0.9 KNFU by gamma M1. So here, when you are considering ultimate stress, the partial safety factor we have to use is gamma M1. So let me show you that. So when you are using resistance governed by ultimate stress, gamma M1 would be 1.25. So let us write. So gamma M1 we have 1.25. AN is net area. So if you see this, so this is a critical section. This is the critical section. So when you have to find out this area, let me draw cross section here. Cross section, it has 3 holes, 3 bolts. So when you have to calculate the gross area, simply this is B, this is T. Simply B into T. But here we have to subtract these 3 hole widths from this entire width. So that will be how many holes we have? 3 holes. Or number of holes we have into D naught. That is the diameter of the hole multiplied by the thickness. Let me write it here. AN is B minus ND naught into T. So B is 300, is the width of the plate, minus we have 3 bolts, hole diameter is 22 into thickness of the smaller plate is 10. So we will be getting the value as 2340 mm square. And here Fu we have ultimate tensile strength of the plate 410 Newton per mm square. So let us substitute all the parameters we have. We can find out TDN, which is equal to 0.9 into a net area is 2340 mm square into Fu is 410. By partial safety factor, gamma M1 is 1.25. So we will be getting it as 690.768 Newton. So that would be 690.768 kilonewton. That is absolutely again greater than the load, which is design load 500 kilonewton applied load. So it is safe in this case also. So we have to find out the third one, the design strength due to block shear, TDB. We have actually 2 values, TDB1, TDB2. So let us write the values of TDB1, that is AVG into, this is also page number 33 of IS 800. You can just write from it. Need not to remember anything, I have already shown you that. M0 plus 0.9 AN FU by, sorry, this is AVN FU by gamma MM. And we have TDB2 0.9 AVN FU by root 3 gamma M1 plus AVG into Fy, sorry, this is ATG, this is ATG by gamma M0. So let us find out all the parameters here, whatever are required. So here the AVG is, so let us first know what is, let us have an image of this. So this is the only plate I am drawing. It has 6 bolts like this. So here it is 40, here it is 60, and here it is 40, and here this is 110, here this is 110, again here is 40 according to our design, the previous diagram. So block shear strength, we have to find out AVG is a, V refers to the shear force. So we have to find out the shear, gross shear, G refers to the gross. So always shear acts parallel. So let me draw it here. So here So this is our shear line. How many shear lines we have? We have 3 shear lines. So let us find it out. Yeah, so you have 2 shear lines. So in this manner, actually this will cut into 1, 2, 3, 4. So this block will be cut off. So let us try to find it out. Or 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. So this is the part it will cut. So we have 2 lines, shear lines in the critical section which are near to the edge. So let us try to find it out. AVG is we have 2 into this line length is 40 into 60 multiplied by 40 plus 60 multiplied by the thickness of the smaller plate which is 10. So we will be getting it as 2000 mm square. That is AVG. So now we can find out AVN. AVN refers to the net. So we have to subtract these whole areas. Here the whole full hole and here this is a half hole. Up to center of the bolt we have to consider. So we have again 2 lines. So again 40 plus 60 as usual minus the bolt holes. That is one bolt hole that is 22 minus 1/2 that is 22 by 2 into thickness of the plate that is 10. So we will be getting it as 1340 mm square. Now we have to find out ATG as a tension. So that is the tension will occur in a vertical line. So this is our tension line, right? So that is simply how much it is. The length is 110, 110, 220. So let me write 110 plus 110 multiplied by the thickness of the plate 10. So we will be getting 2200 mm square. So when there is ATG, ATN we have to find out. ATN we have to find out. That is ATN we have to subtract the bolt holes here. That will be how much? 110 plus 110 minus how many we have? One full hole this is, right? That is minus 22 minus we have half hole here, half hole here. That is 2 into 22. I mean 22 by 2. Okay, let me write it in the same time. Into thickness of the smaller plate. So we will be getting it as 1760 mm square. So if we have this, we can easily find out these 2 values. Let us substitute here. So TdV1, if you find out AVG is 2000 into FU is FY, we have 250 by root 3 into gamma m0 we have 1.1. We have seen in the previous steps 0.9 into we have here ATN. Here this is 1760 into FU we have 400 by gamma m1 we have 1.25. So we will be getting the value of TB1 as 781983.94 Newton. So that is 781.983 kilonewton, 984 kilonewton. And here we have to find out TdB2. Let us substitute all the parameters here. 0.9 into we have AVN as 1340 into FU as 400 by root 3 into gamma m1 we have 1.25 plus ATG we have 2200 this is ATG into FY we have 250 by gamma m0 we have 1.1. So TdB2 we will be getting the value as 728.381.29 Newton. So that is 728.381 kilonewton. So if you compare, this is also greater than the design load which is 500 kilonewton. This is also greater than the load 500 kilonewton. So ultimately if you compare only the design strength, and this is absolutely safe, whatever the design we have provided is absolutely safe. And if you take only the design strength of the plate, we have to compare the lesser value compared to all TD. So if you see very clearly, TDG is having very less value, 681.818. So that would be the design strength of the plate. That's all. Thank you.